I'll try and keep this talk informative, even if you don't care about the low, kind of development details of the container runtimes. I think it'll be interesting in the sense that I'll try and walk us through why serverless is interesting, where we've been with servers, because as you know, we've been dealing with servers for a very long time in the tech industry. We've been trying to find ways to manage them better, more efficiently, pack more applications on them, deal with security constraints and issues. And we've really, walked through a bunch of technologies over a period of the last decade to try and solve those problems and those challenges. VMware was just standing up here. They're kind of the linchpin of that movement from bare metal to virtualization and all the excitement that brought about packing all these OS images on a single physical server. We went from that to sort of the cloud era of IaaS, and right now, maybe if you follow a bunch of people on Twitter, you're seeing tweets from the OpenStack Summit in Boston happening right now. Dan was up here before lunch talking about platform as a service and Cloud Foundry, which again was another angle on how do I get my application on a server. Containers came 3-4 years ago, at least the Docker model of what it means to interact with containers, and Vincent Batts was here early in the day to talk to you about how that's really just a consumption of a bunch of Linux kernel features that have existed for well before Docker and kind of the current container ecosystem existed. And from that, we've obviously moved into orchestration. You've heard Kubernetes talked about multiple times here today, Docker Swarm, Mesos, and obviously there's other players in that space. As you can tell, twice we've seen the huge ecosystem picture with everybody's logo. And now, just maybe in the past, year, depending on how much you keep up with the industry, you've been hearing about serverless and this functions as a service space. And probably the iconic picture of that is this is Tim Wagner at not the serverless conf that was, I think, last week here in Austin, but a year ago in New York City. He is physically smashing a server on stage to much dramatic effect of the bye-bye to the server era, and now we're all going serverless. But of course, there's still servers, and that's, I think we all know that. There's been much made about this term and the terminology used, and a lot of mockery on Twitter of the whole serverless kind of paradigm. But really, it's a shift. Again, I just listed off these technologies. We're always trying to find ways to get our application or the code we want to run in the cloud, run it most efficiently. And serverless, maybe better term functions as a service, is really just a shift in our focus to stop thinking about how to package my whole application and all its dependencies, but I'm just going to write a function. I'm going to register it with some framework, whether that's AWS Lambda or OpenWhisk or Google Cloud Functions, and then I'm going to use that system's set of triggers or actions or events to drive my code. And because now my focus as a consumer of your serverless platform is really around my function, these serverless servers matter maybe more so than ever. Because now you, the user, expect basically infinite scaling of my function. If I want to run it 100 times or 10,000 times, or every millisecond fire a function, you as the provider of that infrastructure have to figure out how to support me doing that. And I also have this expectation that my function never goes down. Again, it's not a server, it's not an instance, but I want my function to always be able to run. And so you, the cloud provider, have to figure out how to do that. And again, importantly to me, the consumer, I only want to pay when my function runs. The whole thing that you intrigued me about when you told me about serverless is that I no longer have to pay to have an EC2 instance up all month, or some other VM instance on my Google Cloud. I only want to pay when my function actually executes. And so before we jump into why container runtime is important, if you haven't looked at the pricing model around functions as a service, this obviously gives you the clue as to why we care as a cloud provider about how long it's going to take to get your function executed, because I'm going to charge you based on how long your function ran times the memory allocated for that function in gigabytes. And so there's this new gigabyte second term that if you go to Amazon Lambda, or if you go to IBM Bluemix and look at our OpenWhisk pricing or Azure Functions, you're going to see a very similar pricing model. And so back to those servers, all of these public cloud providers have to manage the registration, the runtime, the execution, the pricing, and charging of those functions. And so, again, these servers are critically important, how they're operated, how they're run. And because I work for IBM and I work with the OpenWhisk team, the one I can talk to you about is the Apache OpenWhisk project. It's an open source project that came from an IBM team who did the initial implementation. Adobe showed interest in it, joined together with us to contribute it to the Apache Foundation. You can go to openwhisk.org and read more about the overall project. But IBM Bluemix is our public cloud, and we operate OpenWhisk as a service in our cloud. And so in the architecture of OpenWhisk, the initial creators of the project said, hey, containers make good sense as the actual invocation vehicle of my function. And so I don't have time to talk through the entire architecture of OpenWhisk, but as you can assume, there's a lot of moving parts. Again, as you get less sort of responsibility on your end, the cloud provider obviously has more responsibility to handle logging, the crashes of the container or the runtime that's running your function, how to invoke it, how to handle events, how to handle all of the orchestration of that together. And so in this case, the invoker is actually using the Docker engine. And one of the nice benefits of that Dan mentioned in his talk is in OpenWhisk, you can actually bring a Docker container as your function. And so you're not limited to the language support that OpenWhisk has. You can obviously write in Swift or Node.js, but you could also write a C program, compile it, put it inside of a Docker container, and submit that to OpenWhisk as your action. So again, that was an interesting choice early on, giving this added benefit that anything you can package as a container, you could provide as a function. But obviously the life cycle of the entire Docker engine may not be sufficient for the kind of performance guarantees that we want. So, again, maybe thinking in your laptop sense, I write a Docker file, I Docker build, I Docker run, it does something interesting, now I Docker RM to remove that. If that takes a few seconds, that's no big deal to you. In this world, if we're going to charge you per 100 milliseconds, all of a sudden, every second that we waste is actually on us and our infrastructure to handle that we're not charging you. So the good news is that we really have options today. This kind of stack picture came up in Patrick's talk from Docker earlier today. So the nice thing is, if you've been here all day, you already have a concept of this. But from about Docker 1.11, just over a year ago, the Docker daemon started to be split up, and we continue to work towards splitting up this sort of monolith of a container runtime engine into some components, and most importantly, Containerd, which has now been contributed to the Cloud Native Computing Foundation, and runC, which Vincent talked about early in the day as part of the Open Container Initiative. Both these pieces are, in essence, what drives the container. And so if you think about it, I now have a choice to use the Docker engine and its whole ecosystem around that. If I want to use Containerd and interface it with its gRPC API, and we'll talk kind of about where that's going a little bit. Or maybe I just want to use the runC binary, which again, now I have more responsibility on my end because runC doesn't have the concept of image delivery through a registry. So again, I have to do a lot more setup as I move down this stack. But this gives us an interesting case study for as I build this serverless platform where I've decided containers are the proper invocation vehicle. I don't necessarily have to use Docker. I could also choose Containerd or runC. Many people obviously should be aware of what Docker is, but obviously you have a broad set of capabilities that's more than just executing a container. It now has orchestration through Docker Swarm. It has this remote HTTP API. It has support for plugins. It has libnetwork that was just mentioned with now you have overlay networking and pluggable capabilities there. I can actually build images. I can push them to registries. So again, Docker kind of gives you this full runtime ecosystem of capabilities. Containerd is sort of one step down from that. It has a gRPC API, and there's really, it's probably worth taking a second to talk about Containerd past and Containerd future. Containerd existed, as I mentioned, since just over a year ago, but in December of last year, Docker announced they would be contributing it to a foundation, which has happened. The CNCF accepted Containerd, and that was announced at the Cloud Native Con in Berlin just a few months ago. But part of that contribution was to make Containerd a more complete runtime, so adding the image registry interactions and sort of more of a complete lifecycle story around Containerd such that it could be embedded within a larger project that really just needed embedded runtime. And so you may or may not have seen that Kubernetes now has activity to, with their CRI interface, implement that using Containerd, which would allow them to not have to run the full Docker engine underneath a Kubernetes pod. Below Containerd, obviously there's runC, which again just takes a piece of JSON, which specifies what I'm going to run, how I'm going to run it, what namespaces I want. There's no network support, there's no image registry interaction. I have to have my root file system already unpacked in a directory, and runC will do the rest. So given those three layers, to help the OpenWhisk performance team try and figure out what's the best case scenario, what should we use, how performant are these different pieces, how can we determine as we make changes which one improves, which one's better for different scenarios. So they already had some scripts that they've been using, but it seemed worth time to actually implement a tool that we could use that I've called Bucket Bench for lack of a better term. It's out on GitHub. But effectively, Bucket Bench says, I can drive a container runtime. It supports Docker, Containerd and runC today. Tell me how many threads you want to run, what image you want to run, and then a benchmark set of operations. So start, stop, remove, or pause, unpause. And Bucket Bench will do that. It'll drive the container runtime given the benchmark that you provide, and then provide output such that you can now compare, over a series of threads, how many containers per second throughput did my different benchmarks against different engines take. And really, again, the goals of this project were not just straight through performance, but really also to assess runtime stability, because running multi-threaded against the Docker engine, depending on what release you were on, you might find various errors being thrown and issues with trying to remove right after a container exited. So there was both the runtime stability, but also that straight through performance. Obviously, as you change configuration, so again, run C, you have this config file where you can constantly be changing which namespaces to create, how much memory, my image config. Obviously, you can significantly impact your numbers by changing those configurations, and then simply by changing what's installed on the tested system, we found great differentiation in stability and performance just by walking through the Docker releases over the last year. And some of that's due to work we've actually done to contribute changes to the engine as we found issues through this project. I'll take you through a very, very quick look at Bucket Bench. Again, this may be kind of outside of your area of interest, but hopefully when we wrap up, there may be things that are interesting for you to follow up. But the project itself, quite simple, 2 major interfaces that can be implemented, a driver interface and a bench interface. And so benchmarks define that set of operations that you want to operate. A driver, any container runtime that can handle run, stop, remove, pause, and unpause. Again, I've done that for Docker, Containerd, and Run C, but that could easily be extended to things like Rocket or even LXD from Canonical. Any runtime that will support that set of operations could have a driver interface, and then benchmarks can be run against any of those drivers without the benchmark having to know which driver it's running against. Obviously quite simple and straightforward. But it's one thing to get a bunch of numbers out of a tool, to be able to say, well, Run C can run more containers than Docker Engine in the same amount of time. That's interesting, but it's more interesting to find out why. And that obviously was the more complex problem. Simply writing a tool to run, execute containers was not the hard part. Here, obviously, the Go tooling, for those that are fans of the Go language, given that all these runtimes I'm talking about are written in Go, then all the pprof and tracing capabilities of the Go runtime are available here, with the caveat that as you're running a multi-threaded scenario with hundreds or thousands of containers being started and stopped, trying to figure out the best way to sort of insert a probe to get just an estimate of part of that time is quite tricky. So if you look at the Bucket Bench source, I've tried to add this notion of tracing optionally, a container every 100th time or 1,000th time to output this kind of information. Obviously, when you're thinking about syscalls and why is when I have 5 threads running versus 10 threads running, cloning to get a new container with certain namespaces takes 5x longer than before. So, getting below the Go runtime to strace, there's some great tooling around flame graphs. That's a Docker run from 1.9.1, so that's quite old, but a good example of trying to see where time is being spent in the engine as it calls down into Linux to do various tasks. So again, maybe just to bring that to a little bit of reality. So, so what that's great. You wrote this tool. It does some interesting things. What have you found? One of probably the most interesting things that it would have been cool to say I found it, but by finding it and then searching, I found out that this is a long-standing issue that many people know about. But creating and deleting network namespaces in the Linux kernel, even in modern kernels, has a significant impact under load to performance. In fact, without creating a network namespace, you can have container start times well under 100 milliseconds. But once you have load, creating a network namespace can take up to 1/3 of a second or a half second, which again, when we're talking about trying to conserve hundreds of milliseconds, that's a pretty big delay. And if you, I'll post these charts. There's a Stack Overflow question about this that links to more information that there's a spin lock with under multi-threaded contention has a known issue. So that's probably one of the biggest things. And again, that's caused us in the OpenWhisk use case to consider sharing network namespaces, because once you create a container that holds a network namespace, you can create other containers that actually just use that network namespace, and you have none of this significant delay. So that's an interesting thought about improving start time performance and getting around this known issue. Obviously, when we're talking about comparing the complete Docker runtime to something like runc, the API overhead of the Docker client calling the server, the libnetwork setup and teardown of, so not just the network namespace, but now giving an IP address and setting up all those things, the metadata that the Docker engine keeps about your container, its state, all these things, which also includes some significant locking in the Docker engine, all add to a pretty significant differential. So you'll see the blue line is runc as the number of threads increases. And again, this is with network namespace creation. These lines, I didn't actually get a chance to put it in here. They almost flatten if you do the shared network namespace workaround. But obviously there's a differential just between using Docker and using something at a lower level. A lot of that has to do with this that I'm talking about, with the libnetwork stack, the locking in the engine to handle metadata changing as you start and stop containers. And then many of you probably know about the graph drivers. So your backend storage, device mapper, overlay, AUFS, depending on what kind of image you're using, how many layers it has, the whole copy on write metaphor used by Docker and other container systems can have a measurable impact. So again, all these things are inputs into us running a serverless framework on a container runtime. It's generated both pull requests upstream to solve things that are fixable, considerations around workarounds for some of this. But maybe you're interested in Bucketbench, maybe you're interested in performance in general. Here's some things that are still left to do in the tool itself. I'd really like a better way to specify a benchmark rather than requiring you to code in Go to say, here's my operations. So maybe some kind of JSON or YAML format. It outputs kind of this nice human readable format, but it'd be better to have structured output and provide metrics on each operation that happens during the benchmark. The tool has all that internally. It's not output today. I need to update the Containerd driver implementation to use the gRPC API rather than the external client binary. And then, if other people are interested in adding other runtimes, there's that option as well. So here's my so what slide. Maybe performance isn't interesting to you. Maybe container runtimes aren't interesting to you. But maybe you heard Dan talk about OpenWhisk earlier. There is a longer form talk that he mentioned tomorrow, 11:50. So again, you can hear more about that serverless framework, what it does. You can, again, if you're interested in Bucketbench, get involved in improvements. And if anyone who is more of a performance expert than I am, which I am definitely not, it'd be awesome to think through ways that Bucketbench could interface with tracing or performance tooling, to have better integration than just trying to figure out how to trace certain portions or certain numbers of containers over the runtime. And then obviously fixing and improving these container runtimes as we find issues. So thank you very much for sticking with me through that. I think there's a break after this. But if you're interested, here's a couple things. I will post these charts on Twitter. My handle is there at the bottom. Love you to check out the project if that's of interest. Feel free to connect with me, ask me questions. And obviously, whatever container runtime you're using, enjoy containers and the growth of this ecosystem. It's been absolutely crazy the last few years, and I'm sure there's a lot more to come. So thanks a lot.